So I want to finish up chapter 2. We're going to be looking at regression. And the idea is that we got to start with a scatter plot. Now, to come up with a scatter plot, we want to try to describe or look for relationship, well, I want to say relationship, association between two variables. So for example, we could let variable x, this could represent temperatures, say in Roswell, for like the first 10 days of some month. So high temperatures. And we could let y be the high temperature in Farmington. So basically diagonally across the state from us. And let's say we're going to look at the first 10 days of some month. It could be, say, I don't know, February. And what we do is we take a look at these. We sort of, in a sense, compare them. So let's say this is Roswell, there's Farmington, and this is represented by the x variable, and this is the y variable. Now this might be kind of confusing because what we do here is when we talk about a variable, we usually use a variable to represent a single number. So we use in algebra, x could be like 3 for, let's say, 2x equals 6. So x is equal to 3. Now I'm going to put up here something a little unusual. And I'm going to put up temperatures for x. And what we're going to see is that x can represent all these temperatures. I'm going to continue the chart down here. So these are temperatures, say, in Roswell, and then I'm going to put in the Farmington ones here since I'm here. So the chart continues on. Now, x and y we refer to as random variables. Now, in algebra, when we talk about x and y, we talk about variables that usually have one value. Now, sometimes they can have multiple values. For example, when you solve quadratic equations, you can get x equal to plus or minus 2, or plus or minus 1, or plus or minus square root 3. And in that case, you could have multiple values. With random variables, you could kind of think of them as like a coin. Like x could be a dime, y could be a quarter. And when you flip x, x will generate, well, either heads or tails. And let's say y is also, say, again, I think we said it was a quarter. So you flip that coin, you could get heads or tails. So x is just sort of, it generates some outcomes, sometimes heads, sometimes tails. And y will generate some outcomes, say, sometimes heads, sometimes tails. And so that's what we mean by x and y. They can output these different random values or random results. So x is going to represent output from one type of random process. Y is going to represent output from some other random process. Now, for both x and y, we decided to see what these variables come up with 10 different times. So x came up with this, and then it came up with this, then this, then this, then this, then this, and this. And then y came up with these temperatures and these temperatures. So What we want to do, though, is there some kind of pattern here? Now, you might say, well, if X is always random and Y is always random, then why would they ever be connected to each other? And you're absolutely right. That doesn't really make any sense. You would sort of assume they aren't. And the way we can tell is we graph them. What we'll do is we'll graph points X, Y. Now, I should be clear here that how do we know which X goes with which Y? Well, let's say this is the first of the month. This is what Roswell was on the first. This is what Farmington was on the first. This is the second of the month, the third, the fourth, the fifth, and so on. So these are the first 10 days of, say, February. And this is, I don't know if this is actually true. Let's say it's February of some year. Who knows? And, well, is there some kind of association between the random temperatures in Roswell and the random temperatures in Farmington? In other words, are the random values that we see in Roswell, well, are they kind of maybe similar to the values you get in Farmington? So the way we look for association is we graph X and Y. So this would be like first day, second day, third day, fourth day. We graph all these days and we look for a pattern. So if there's a pattern in the graph, that might mean there's some kind of association. So let's graph these points. We're going to get like X is 66, Y is 58. That's going to be a point. And then so on. So we'll be graphing points like this. So this would be for the first day, second day, up to the 10th day. And so things we might look for, granted these are random temperatures, and I know in New Mexico temperatures can be all over the place across 10-day period. But you know, if you're, say, looking at temperatures between, say we're comparing temperatures with Roswell and Artesia, well, the random temperature here is going to be fairly close to the random temperature here because they're in the same region. So the random temperature here would be hopefully closer to the random temperature here if we're talking about Roswell and Artesia, but we're talking about Roswell and Farmington. They're far away. So let's take a look. Let's see what happens. And again, I'm being cautious. I don't want to say relationship. I want to say association. There's a difference. Relationship means cause and effect. Here we're looking at really just association. Are they sort of behaving in parallel? It doesn't mean one's causing the other. Again, correlation is not causation. So if we graph these, I'll give kind of a very rough graph here. So I think we got a point right about here. Let's see, kind of low here. And again, you could read these off the chart. I'm not going in order, I'm just sort of filling them in. Hopefully I don't make too many mistakes. There's a point roughly there. Here. Be a little bit off. So these are the temperatures for Roswell. These are the temperatures for Farmington. And do you see some kind of a pattern here? And I don't know, I'll be honest, I don't see one. Not a strong pattern here. So it really seems to look like there's not really any association between Roswell temperatures and Farmington temperatures in this example. Now, let's take another one. Let's say we have Albuquerque and Santa Fe. And again, this will be our X variable. This will be our Y axis or our Y variable. And then 4638. 4941. 5041. 5046. 57. 52. 57. 54. We'll continue down here. 59. 56. 63. 57. 65. 69. And we've got our first day, second, third, fourth, fifth, sixth, seventh, 8th, 9th, and 10th. So if we graph these points, and the points we're going to get, again, using Albuquerque as the x-axis and Santa Fe as the y-axis. Let's see here. Just double check that. All right. So we're going to be graphing points 41, 35, out to 65, 69. So we graph all these points. Again, this will be Albuquerque will be our x-axis, Santa Fe will be our y-axis. And when we do this, we're going to get roughly the following. Again, I want to try to make this as accurate as I can, something roughly like that. Let's see here, below 55. Now, what we see here is there does seem to be a pattern. So again, this is Albuquerque temperatures, and on the same day we have the Santa Fe temperatures. And so you can kind of see a rough linear pattern or line-like pattern passing through that graph. And so that's a pattern. This suggests that the temperatures in Albuquerque are somehow associated with temperatures in Santa Fe. And a good reason you might say this is they're kind of roughly in the same region. It's not like Roswell and Farmington. So this is what we're looking for. We take some random output, and we pair them up meaningfully. So we take the random temperatures of the first day, random temperature of Albuquerque, random temperature of Santa Fe on day one. We pair those up by day. Random temperature for Albuquerque on day two is paired up with random temperature from Santa Fe on day two. And when we plot these pairs, we see there's a pattern. So here's the idea. We're getting at this idea of numerically measuring the existence of correlation. So correlation. In some way, one variable is associated, not, oh, I'm sorry. It's associated with another variable. Again, we're talking correlation. We don't know if there's any causation here. So you got to be careful with that. So basically what we're looking for in our scatter plot, we want to look for a pattern. That's what we want to look for. Now, there are different types of correlation depending on the pattern. So if we have a scatter plot like this, and everything's just kind of all over the place, this generally means no correlation. I'm going to abbreviate correlation. If we have a scatter plot like this, like we just saw, where there's, roughly some kind of line forming here, this is a linear correlation. Again, I'm abbreviating correlation. And then if we have something that has kind of an exponential look, like there's a pattern here, but it's not really a line, like it's doing kind of a swoop like that, this is nonlinear. Now, sometimes when you take a look at scatter plots, you're going to get what are called clusters or gaps. Now, we talked about this before with frequency tables. We saw, for example, with the pennies example, that if pennies were made before 1983, they had a different content from pennies made after 1983. And so that caused them to weigh different amounts. The result of that is when we came up with our frequencies, we ended up getting a gap of zeros in our frequencies. We had a lot of weights that were showing up, and then zeros for some weights, and then more weights showing up. And this gap of zeros, we weren't getting any frequencies at all for these weights in the middle. It was suggesting that you had two different populations, the pennies before 1983 and the pennies after 1983. So the way this would look on a scatter plot gonna squeeze in 3.2 there, really sneak it in there. And then we'll go 1960, 1970, 1980, 1990, 2000, 2010, 2020. What we would get roughly is something like this. We would get some pennies like this. And then in the earlier years, we'll get pennies kind of over here. Now, you might say, and again, this is for clusters and gaps, that there's sort of a line here, but we don't look at it this way. When we have a gap like this, what we're going to do is we're going to look at what appears to be two different populations. And I should label these. These are years. Squeeze in years there. And this is weight in grams. Squeeze that in there. Weight in grams. Again, if you recall, from 1980 on, we had some lighter pennies. And then from 1980 into the past, we had the heavier pennies. I don't think they actually told us that last time. Well, they're showing us now. So we have two different populations. So the idea you might say is, well, doesn't weight have some correlation with year? Isn't it associated? And you could say very roughly in the sense that before 1983 pennies are going to be heavier than pennies that are after 1983. So you see, well, there's a very rough line here. But really, here's the thing. We want to look at the clusters. When you talk about correlation, when there's a clusters, where we have this gap, we want to look at the clusters to determine correlation. We want to look at the clusters individually to determine correlation. And what we're going to see is that in these clusters, there's not very strong correlation. The reason is, we could say for the pennies before 1983, the weight's roughly 3 grams, but you're going to get some variation. It's going to hop around a bit, and it doesn't hop around in a pattern, really. It really, you know, maybe in the same year, you can have some pennies that are heavier than 3 grams and less than 3 grams in the same year. Same thing here, pennies could be kind of on average 2.45 grams, but even in like the same year, some are going to be less than that, some are going to be more than that. So there isn't really a pattern. The only thing we do see is we have two big clusters or two populations where it looks like, this one's kind of centered on 3 grams, this one's centered on 2.45 grams. And then it's all kind of random within those two clusters. All right. So what we're going to do, we're going to look for a numerical measure of correlation. We want a numerical measure of correlation. And so what that's going to be, we're going to use what's called a correlation. A correlation coefficient. And we represent it with the letter R. So I'm going to give you some properties of R here. First off, R is going to be between -1 and 1, and it could be -1 and 1, or 1, either way. What does R minus 1 look like? If you have a perfect linear correlation that has a negative slope, that's R -1. R positive 1 is a perfect positive slope. And then finally, R equals 0, well, everything's kind of all over the place. Doesn't seem like to be any pattern at all. So this is perfect negative. This is perfect positive. I have to abbreviate positive. And this would be 0. Or let me put it back this way, no correlation. I'm going to abbreviate correlation. So you have a perfect negative correlation, perfect positive correlation, and no correlation whatsoever. So how do you come up with this wonderful number? Well, let me show you. So the correlation coefficient for random variables x and y, so we could have Roswell, Farmington temperatures, it's this. Squeeze this one in here. We'll do the same thing with the y coordinates. There we go. Now I'm actually not going to have you calculate it, well, to a large extent. What these mean are sums. So this is, we let I be 1. You have to choose a value for I. So when I is 1, this will be the first x coordinate, the first y coordinate, first x coordinate, first y coordinate, and so on. First. And then when I is 2, second. You're just going to add up the product of the coordinates for the first day, and the second day, the third day, and the fourth day. Well, it's called sigma notation to give you an idea. I equals, say, 1 to 3 of xi would be x1 plus x2 plus x3. Or something, say, like this. Xi, yi, x1, y1, x2, y2, x3, y3. And what these are, this would be coordinates from the first day, coordinates of the second day, coordinates of the third day. We're multiplying the coordinates from each day together. Probably not going to do much with this, but I just wanted to show you the formula. So kind of a gnarly formulas go. So anyway, more stuff. So here's the idea. The closer R is to -1 or 1, then there appears to be a correlation. So the closer R is to -1 or 1, we're closer to a correlation. And then the closer to 0, there appears to be no correlation. Again, the closer you are to 0. Now, in all actuality, in practice, we compute this using a computer. You're really not going to try to calculate this on hand, by hand, especially if you have huge data sets. It's just, you're going to be there way too long. It's much easier to use a computer. Now, the question you might be asking is, well, what's the cutoff? How close does R need to be to -1 or 1 for there to be a correlation? Well, it depends on the problem. Well, the way that the text handles this is you have what's called a critical value for R. Now, this critical value, again, you're going to get this from a computer. And the way it's set up, or actually a table also, that's what we're going to do. So I'm going to say, well, we're going to get it from a computer, and then we're going to check it against a table. And they do have a table in the text, just a small one. And so the table's based on this. You have your number of pairs. So how many points you have the plot. And on this table, there is a critical value for R. And what you're going to do is, well, actually, let me take a look at this. I think I'm getting this mixed up just a little bit. Oh, so let me cross this out. We're going to get the critical value from the table. We're going to use the R value that we get from the computer. So the critical value for R we're going to get from a table. So how do we do this? Well, this thing's going to have number of pairs and then the critical value for those numbers of pairs. That's just going to be given. That's in the chart. That's going to be solid there. We're going to get our R value and compare it to these critical values depending on how many points we had. Let me give you an idea of how this works. So what we're going to do is we'll count up the number of pairs that we have, and then we look at the critical value for that number of pairs. And then we're going to create a number line. And here's the critical value. We'll plot it on our number line. And then on the other side, we have the negative critical value. So if our critical value, say, was, I don't know, -4. Let's see, let me go with something else. I'm sorry, not -4, I apologize. You're going to keep this between 1 and -1. But let's say it's 0.9. We'd have 0.9 here and -0.9 here for our critical value. So let's say we had, well, let's take a look here. We're going to have an example. If we have 5 pairs, 5 points, and our critical value is 0.878, well, this will be 0.878. This would be -0.878. And this is what we're going to look for. Again, we get this from a chart. We look at how many pairs we have, and we look at the critical value for that number of pairs. If our R value, now that's the thing we get from the computer. We get the R value from the computer. If our R value is somewhere between the critical value and the negative version, then there's no correlation. If it's too close to 0, in other words, this region close to 0, no correlation. But if our R value is above the critical value or below the negative critical value, then we have correlation. So let me do an example here, do a couple. So we're going to look at shoe print length versus height. Now, there's going to be a problem here. We're only going to have 5 points or 5 pairs. And sort of like with experiments where you don't have a lot of data collected, you might not see the effect. So we might not see the correlation here because we just don't have a lot of data, if there's a correlation to be seen. .4, 185.4. Let's see. I'm not sure, this might be centimeters. I think this might be, yeah, this is centimeters. So we got our 5 pairs. This could be X and this could be Y. So if we graph these, (27, 28, 29, 30, 31, 32. 172, 174, 176, 178, 180, 182, 184, 186. So if we graph these, and again, I'm going to be very approximate here, roughly right around there. 75 and 78. And then 75, and 85. So roughly like this. And you might say, well, it certainly looks like there's a pattern. I mean, if we didn't have this point here, it'd be pretty close. And certainly if you had these two missing, golly, we got a line, but these two are part of our data. So if we calculate the R value, again, we would use a computer to do this. You get an R value of 0.591. So do we have a good correlation here? Well, we have 1, 2, 3, 4, 5 points. So what we're going to do, we're going to look on our table in the text. This is going to be in section 2.4. And let me get the page number for that. Let's see here. So it's going to be page 71. That's where you get that chart. And this is what we're going to see. If we look at page 71, for the number of points being 5, the critical value, again, we get the critical value from the chart, is 0.878. So if we put this on a number line, 0.878, and then look at the negative version over here, put that one in there. This is the region between those is where there's no correlation. On the outside is where you get correlation. So our R value is, well, it's on the inside. So this is the no correlation zone. So this means that we don't have a correlation, at least using this method. So it does not appear to have correlation. Now again, this was the length of a shoe footprint and how tall somebody is. So does it make sense that the length of that footprint should be associated with how tall somebody is? Think as someone gets older. When you're younger, you have shorter feet. And as you get older, you get bigger, you get taller, you have longer feet. So, golly, though, but you got the results, there's no correlation. Well, again, though, we want to be careful. We only had 5 points to work with. And, well, what if we had more points? We'll take a look at that. Now, another way of doing this is a p-value. Now, the critical value of R, we get that from a chart. P-value is computed. It's computed with the R value. And again, if you're using a computer, it'll produce this for you. So, for example, let's say let's see here. I'm trying to see their example here real quick. So let's say for your R value, get 0.294. Now what we do is we convert this to a percent. And to take a decimal to convert it to a percent, you multiply by 100%. So this will become 29.4%. So what this p-value will mean, there's a 29.4% chance that of the observations occurring by chance. Check my spelling on occurring there. Got an extra R. Now, in other words, what we're seeing in our scatter plot is a 29.4% chance of that turning out that way. And in statistics, we don't really consider that exceptional. Usually, we want a p-value of 0.05 or 5% or less. In other words, we want the likelihood of this happening by chance to be really small. The percent that this happens by chance, we want it really small. The more likely it happens by chance, well, I mean, there's no pattern that we're actually seeing here. It's just the way these points fell, they just kind of fell that way. And that's actually considered a pretty good chance to see what we see. What we want are very small percentages. We want some very unlikely outcome. Very unlikely. So let's go back to our footprint example. Now, the issue here was the number of points. There was only 5. Now, let's suppose or I should say shoe print. Let's say we have 40 pairs instead of 5. What happens? Well, I'm not going to graph it just for the sake of time. And let's see, I don't know if they actually do have it. You can see it on page 72. You can see the graph, and it's much more linear looking. So for the data that they got, let's see. So the R value, well, that came out to 0.813. There were 40 points, n equals 40. And if we take a look at the chart, oh, okay, we don't have the chart on it. They're not going to give us that one, I don't think. Yeah, we don't have the chart, that much of it. Instead, we're going to use the p-value. And if you do this on a computer, and again, you'd have to use software to do this, your p-value comes out to be, let's see, well, they gave you a range. Actually, no, they didn't. Is it p-value 0.000? So what does this mean? Well, again, the larger the percent, the more likely you could expect this to come about sort of just randomly, happen by chance. So again, if you look on the pattern on page 72, the pattern looks roughly like this. but you'll get a very clear linear pattern. And so the R value, it's 0.813. Before it was like 0.59. So 0.813, this is much closer to 1. And so we have a much stronger linear relationship. And the p-value, the chance of this, well, occurring by chance is highly unlikely. It's 0. Jeez, I mean, they're saying this just doesn't happen. And so that gives us strong evidence of correlation. So that's the idea. We can use the R value and just is it close to 1 or close to -1. If it's close to 1, it has a sort of positive slope. If it's close to -1, you have a negative slope. We could use these critical values where you look at the number of points that you have, look up the critical value in a chart, and then plot it on number line, 0, critical value, the negative version of the critical value. If the R value is between the critical and its negative version, you don't have correlation. If the R value is on the outside of those, you've got a good correlation. Or we could use a p-value. And roughly, if we get a p-value and we calculate it with our R value, it's with the software that we use, the p-value, if it's very, very small, like below 0.05 or below 5%, that's pretty good evidence of correlation. So that's the idea. Now, you've noticed I've been drawing these lines, and there's actually something to these. And that's what I want to get into next. This is called regression. And the idea is this. We want to match a line to a scatter plot showing linear correlation. I want to match a line that sort of works its way through the center of those points. And the idea is that we're going to come up with a line like this. Now, here's the thing. If you remember from algebra, x represents an input. So you give an input number, say you pick 3. And then you multiply it times whatever b1 happens to be, add whatever b0 happens to be. You get an output, y hat. Now, why does y get a hat and x doesn't? Well, the thing is this. X will be the random variables of the x random variable. So in our Roswell versus Farmington temperature examples, x would be all the temperatures from Roswell. Now you might think, well, okay, Farmington was the y value, so wouldn't this be the Farmington temperatures, and why do you got to calculate them? And well, it actually isn't Farmington. You see, what happens in a linear regression, and that's another way we call this, we'll call it linear regression, because it's regression, a regression line for a linear correlation. We'll have x, so I'll call this x1, x2, and this could be y1, we'll call this x3, here, here, and here. And this would be y1, make this one a little bit up here, say y2, drop this one down a little bit, say y3. And so, and here, I'll throw an X4 in here, why not? So okay, these would be different temperatures of Roswell, day 1, day 2, day 3, day 4. Day 4 is kind of cold. And this was the temperature for Farmington, day 1, day 2, day 3, day 4. And we get these points. So the day 1, the day 2, day 3, and day 4. So we fit a line here. And here's the idea. When we come up with this line, we're going to construct it using the temperatures in Roswell. But what's going to happen, because this line really isn't going to hit any of the points, it'll have coordinates using the Roswell temperatures, but the Y values, since we're using points on the line, not the original points, the Y values become different. So what happens, for example, this point here would be x2, y hat 2. It's the y coordinate of this point on the regression line. So that's what ends up happening. And let me make this a little easier to see here. Squeeze that in. So we get to keep the x coordinates, but the y coordinates, they're going to be of the point on the line. So that's y hat 2. So a line, again, it approximates the locations of these points. So that's why this is given a different symbol. All right. Now, where do we get B1 and B0? Well, they are from computers. And what they are, here's the formulas for them. B1. This is another of those sigma sums. It's an x data point minus the average of all the x data points. We're going to talk about that in the next section. And then we're going to have multiplied by y1 minus the y average of all the y data points, divided by let's see here, we'll square that. So that's B1. B0, well, we need B1 to compute B0, so we got to compute this first. And then xi divided by n. N is the total number of points. That's what that n was in the correlation formula as well. The R formula was the total number of pairs. So there you go. Again, I'm not going to, most likely won't have you do this by hand, at least not often. So, but again, usually it's from a computer. So if you take the data from our shoe print versus height example, and you run that through a computer. So again, shoe print versus height. Well, we're still working with this example. We started out at n equals 5. We got really kind of a crummy R value. What did we get there? Let's say we got 0.591. But then we bumped it up. We bumped up our data, collected 40 pairs. So what I mean by 40 pairs, 40 shoe lengths, and for that same person, we have a height for them as well. So you have a pair of shoe length and height, we have 40 of them now instead of 5. And when we did the R value for this, again, if we had done it using a computer, we get 0.831. So in our computer, we can have an option that lets us compute that line. And so what it'll compute is B0. Now B0 is the y-intercept because it's not multiplied to x. So that's going to be 93041. And then the slope, which is B1, that's what's multiplied to x. Remember, your slope is always multiplied to x. Slope B1 is 3.218561. And so that means for our line, and they round it off here in the text, but we're going to get y hat is going to be about 80.9 plus 3 point, let's see, how far did they go? 3.22x. And again, this would come from a computer. Or put another way, height. And this is the idea. Again, we don't have causation here. But we do have an association. We don't have causation, but there is some kind of association. And the association is we can roughly predict a person's height if we know their shoe print length using this formula. So let me say that again. We can predict the height using the shoe print length, and that's the idea. And this is going to be very useful. You could use these kinds of models. You can call this a statistical model. And you can use these kind of models to predict all kinds of things. So here, if you see a shoe print, you can measure it, plug it into this formula, take the shoe print length, multiply by 3.22, add 80.9, and you should get a decent estimate for the height within some error. And the result of that is, well, you have some rough model. Now, does shoe print cause height? Remember, this is shoe print length, not foot length. So, I mean, someone could be wearing clown shoes and could throw this off. Maybe someone's walking on some kind of a shoe that does something like this, sort of funnels down for whatever reasons. Well, so you do have to be a little bit careful, but that this causes height, well, that's probably going to be better left up to science to figure that out. But based on just observations you see around you, this might be a good model to go on. And based on our R values, for our R value, that probably, it's pretty close to 1. Again, the p-value for this was 0. In other words, a very low % chance of happening, pretty much non-existent. It's happening by chance, so this must be pretty strong. So that might be a good model. And if you're doing anything like, say, finance, or if you're doing predictions, say like, I don't know, maybe you're trying to predict the product price of something. Again, that, you get those high R values and that really low P value. That might mean you have a pretty good model and you can make some predictions. Now, the thing with predictions you want to be kind of careful of, when you have these points, it's pretty, you're going to have a very good model for predicting values between, say, x1 and xn. Here you're going to have a pretty good chance to get some fairly accurate predictions. Where things get a little dicey is when you start trying to predict beyond your largest value or below your smallest value. You gotta be kind of careful there. So just a word to the wise. All right. But you can go a little bit out there is kind of okay. So that's it for regression and scatter plots. If any questions, let me know.